Alright, so in this video lesson, I am going to be showing anyone viewing the lesson how to use a chi-square test to test for independence of two categorical variables. But so before we can really get into understanding how to use the chi-square test, we need to understand a little bit about what it means by being independent of two categorical variables, and especially what categorical variables are. The best place to see and understand categorical variables here is to see that through a two-way table. So let me now bring up a two-way table. And it should be similar to any of those two-way tables that we have done during the time that we were studying probabilities. So now, back in those lectures where we were learning about probabilities, then a column of any two-way table was generally regarded as an event of a probability problem, and so was any of the rows of the same table. So this table here describes a sample of 300 children in their teens, which is the number indicated here. And among these children, we study what their favorite TV show is. So for example, the columns here are indicating some children among these 300 children here favor to watch Lone Ranger as their favorite TV show, or another way of saying, some children among these children in the sample prefer viewing Lone Ranger as their favorite TV show, and some other children prefer watching Sesame Street as their favorite TV show, and the other children prefer to watch The Simpsons as their favorite TV show. So the columns here represent the different preferences in viewing the TV shows that are found within the sample of 300 children here. And the rows here on this table represent the different genders. So in what we have here among the children, 100 of them are the boys and 200 of them are the girls. And so these count, for example, in this count right here says they are among the sample here, there are 50 boys who prefer watching Lone Ranger. And say, for example, in this count right here, in this sample it says there are 80 girls who prefer watching Sesame Street as their favorite TV show. So the columns represent its own kinds of events, and now the rows are also creating different kinds of events. And so now this is how I see it outside of probability, or a little more advanced than probability understanding. And now back on my writing board, this is how I understand about the two-way table that we have seen now. So among the 300 children here, then any one of those children can be a viewer who prefer watching Lone Ranger. So now if a child is one of those who prefer watching Lone Ranger as a TV show, then this is referred as a category. And so, but then, outside of being a viewer who prefers watching Lone Ranger, some other child can be a viewer who prefers watching the Sesame Street as a different TV show. So this is a different category. This is another category. And then outside of these two categories, some other children can prefer to watch The Simpsons instead of those other two TV shows. So this is another category. So back then when we were studying probability, we referred to any of these as an event. So this is an event that a child prefers to watch in the Lone Ranger, or there's an event that among all the children in our samples, there's a child or some children prefer to watch the Sesame as a TV show, as their favorite TV show. So these are all events. Or some other child favor to watch The Simpsons. So any of these is an event back in our understanding regarding probability. But now we see these as different categories because we can simply give counts. So these are all the different counts right here. So in the whole 300 children that we sample, then 100 of them, including boys and girls, are those that favor watching the Lone Ranger TV show. And we have another 110 among these children that favored watching the Sesame Street. And then there are about 90 of those children favor watching The Simpsons. And so in the end, I can see any of these, the Lone Ranger, the Sesame Street. These are all different values. Any of these are values of a categorical variable. So now let me write this in red ink right here. The values of a categorical variable that we can name that variable maybe viewing preference. Okay, viewing preference. That even back on my table here, it is also named as like that. So among the children in our sample here, there are 3 different viewing preferences. So some children prefer to watch Lone Ranger as a TV show, and again, some other children prefer to watch Sesame Street, and some other children prefer to watch The Simpsons. And let's assume, in the simplest case here, let's assume that we don't do the kind of problem where the same child, any same child is having equal preference between Lone Rangers or Sesame Street, for example. We don't do anything like that. So my bottom line here is that when a child is categorized into one of the 3 categories here, then that child stays in that one particular category. And so now back to our understanding here that I'm trying to break it down, then being a viewer who prefers watching Lone Ranger, or being a viewer who prefers Sesame Street, or being a viewer who prefers The Simpsons, watching The Simpsons. Any of these categories is just one value. So any of these is a value of the bigger level that we call the categorical variable. So these are the different values. To see the idea now, viewing preference as a variable. Okay. According to this list right here, there can be Lone Ranger as one of the preferences. There can be the Sesame Street, or there can be The Simpsons. We can even have more categories out there in this variable, but this study only focuses on 3. So this variable here in our study of this table only has these 3 different values. So this is the variable, and these are the different values of the variable, the different values that this variable can take. And so these are the categories or the values of our variable, where we put them in the columns as we have seen in our table here. So the columns here, the columns that we have here list down the count for the different values. So these are the different values of our variable. The rows here in our table, and that's why it's called a two-way table. So the rows are also listing the values of a different variable. So the variable are not clearly labeled here, but in how I see it, boys and girls, we can refer to any of these 2 values, as the gender of a child. And so now in this table, I see another one, another variable, another categorical variable. So any child we're looking at in our sample can either be a boy or be a girl. And so this is a category. And this is another category. And back in the time when we were learning about probability, we referred to these as events or event of a probability question. But now again, in how I see it now, being a boy or being a girl is simply a value, or all of these are the values of another categorical variable. So we actually have two different categorical variables involved in our table here. And so values of another categorical variable. And this variable now, how about let's call that, we can name that gender. Gender of any child in our sample. And so now, as a bottom line, anytime we are given a two-way table, then anyone working with the given two-way table can see one categorical variable being represented along the columns or among the columns of your two-way table, and we can see another categorical variable being represented among your rows of your two-way table. And any of those columns are before the total column, and any of those rows are before the total row down here. And so a two-way table, any two-way table, is the best example where we can see the existence of categorical variables, specifically two of them. And so now for a two-way table like this, then usually we would like to use a two-way table to recognize whether or not our two categorical variables have any kind of relationship. And really, I mean any kind. So one way I can try to point out that, hey, let's look at the Lone Ranger category here, for example. So for within those children who prefer watching Lone Ranger TV show over here, will it always be, or is it only in this table that the number of boys and the number of girls are about the same when it comes to watching Lone Ranger? So what I mean now is that in this table, it evidently shows that for a Lone Ranger viewers, then the count is equal between the two genders, the boys and the girls. But will it be the same? That's what my point is. Will it be the same with other tables? And so if we find other samples of 300 children and under the Lone Ranger category, we recognize again about the equal count here for viewers among the two genders who watch the Lone Ranger, then that would imply some kind of relationship between being in one gender and how it affects, how it relates with your viewing preference. And so that's one way of how I see a relationship. Or in another way, let's now focus among the boys here. So in the way how this table shows, I see that we have the highest count in the boys who prefer watching Lone Ranger. Whereas in the Sesame Street, there are only 30 of them among our total count in the children sample here. And there are only 20 children who prefer watching Simpsons among 100 of these boys in our sample. And so outside of this table, will it also be the same for on any other samples of 300 children, boys and girls together, that we will always have the most, the highest count of boys who watch Lone Ranger? So any of those that I have pointed out can be an example, can be a way to see some kind of relationship between the two categorical variables here. And so in that way, as long as we can recognize one kind of relationship, doesn't matter which, or it could be all different ways of relationship, but as long as there's one kind of relationship between the two variables, the viewing preference and the gender, as long as you can see a pattern and can generalize that to other tables, to other sample tables outside of this table that we have, then we can say that the two variables are dependent. And so two categorical variables. Okay, and of course, in what we're within within our study here, we're studying that through a two-way table. So to be clear here, I'm going to say two categorical variables in a two-way table. Okay, so any two categorical variables are dependent. So the term I would like to first introduce. So two categorical variables are dependent. If there is any kind of relationship recognized between the two variables. And so when I'm saying if there is any kind, because back on the computer screen I was explaining there could be a lot of different ways how we can see a relationship existing between the two variables. So as long as we recognize there's any kind of relationship, maybe just one or maybe two, or maybe there's so many different ways of how the two variables relate with each other, then the two categorical variables there are being referred to as being dependent. Okay, so again, two categorical variables, and primarily we focus in any two-way table, are referred to as dependent if there is any kind of relationship recognized between the two variables. And so now in that way, in our understanding, that we started out understanding what it means by the two categorical variables are dependent on each other. Then on the other hand, independent now. Independence on the opposite means not dependent. Independent is exactly the opposite of dependent. And so as a clear definition, so two categorical variables and in a two-way tables, of course, in a two-way table, of course, are independent. If allow me to use some formal term a little bit, but if no relationship can be proven between the two variables, and no relationships can be proven between the two variables means, think about the table that we have had here again. Maybe we recognize here that for Lone Rangers we will have equal ratio between boys and girls who favor watching that TV show, but maybe that's only happening in this table of ours. Other similar table of 300 children and being arranged into two different categorical variables like this, maybe we find different counts that do not reflect equality here. And so that's what it means by we fail to prove that the Lone Ranger and boys and girls have a relationship. So that's what it means, like the independence between the two categorical variables means if we cannot find any relationship at all, or none of the relationship can be proven between the two variables. Maybe it's found in some table, but in other table it's different again. And so that's what it says right here. If no relationship can be proven between the two variables, that's when the two categorical variables are independent. And so to keep it short, And a lot of time I highly recommend my students to understand the idea, to start understanding the idea of independence by first understanding what it means by being dependent, and then independent is just the opposite way around. All right, so after observing our given two-way table and seeing some explanation about what it means to have two categorical variables as dependent or independent, then the following question is brought to us right here. So let's spend some time reading the question. And so now, admittedly, I am going to use this exact table and proceed further with it as an example of how we can do a chi-square test for a hypothesis about independence. And so now allow me to get started into reading the wording description of our question here. So at significance level, recall for yourself that alpha here means significance level. So at significance level, alpha equals 0.001 is the sample. And so the sample is apparently the given table that we have been looking at, that we have been investigating. So it's the sample as the given table showing strong evidence that the viewing preference and genders are dependent. And so at this point, I have to be clear. It is highly recommended that this video lesson is to be viewed after you have had some experience or have had some learning about how to test a hypothesis in general. And so assuming that you have already had some experience or have had some learning how to test a hypothesis, then this way of how the question is worded is the sample showing strong evidence. Immediately that way of wording, that style of wording immediately rings a bell for us that the problem we're about to do now is going to be a testing of a hypothesis problem. So now I am going to get back on my writing board right here and let's try to tackle down our two hypotheses. Because now as soon as we identify that our problem here is a testing a hypothesis problem, then we can immediately try to identify where our null hypothesis and our alternative hypotheses are. So let me now quickly rephrase this. According to the statements right here, it says that we're trying to prove that viewing preference and genders, these are the two categorical variables that are found in our two-way table. So the viewing preference as a categorical variable and genders as another categorical variable. The statement in our question is stating that viewing preference and genders are dependent. And let me now underline this term dependent right here. And again, let me quickly swing back to the computer screen right here. And we're trying to prove, or is the sample showing strong evidence that viewing preference and genders are dependent. And so this is the statement that I directly copied down from the computer screen right here, from the question that was brought to us. So now, utilizing our experience from testing a hypothesis, then the general idea we have learned from testing a hypothesis now is that anytime we read the wording of our question, then that direct statement being stated in our question, this statement I'm highlighting in yellow ink right here, is the statement we're trying to prove. And so now, from what we have learned about testing a hypothesis, with this statement as the statement we are trying to prove, we can now regard to this as H1. This is some experience that we have learned through testing a hypothesis in general. So viewing pref and genders are dependent. This is a statement we're trying to prove according to the way how it was worded in the question. And so I can simply take that as H1, the alternative hypothesis. And now, if we chose this statement directly from the question to be H1, then if we look back, if we search back in our experience in testing a hypothesis, then the way how it has been is that the null hypothesis and the alternative hypothesis here are always the opposite of each other. So if our current alternative hypothesis is saying that viewing pref and genders are dependent, then now it makes perfect sense for us now to say that, to come up with the following statement: viewing pref or viewing preference and genders, almost exactly the same statement, but now we're saying the opposite. Viewing pref and genders are independent. So now two statements arguing against each other, and once we have identified this statements down here that came directly out from the wording of the question, and it's saying that we're proving the two variables here are dependent, then now we can call this other one where it says the opposite way, now we can regard to that as a h sub 0. And so now viewing preference and genders are independent. That's our null hypothesis. Whereas viewing preference and genders are dependent. It's a counter argument. It's our alternative hypothesis here. And so in that way, now we have successfully found for ourselves the two hypotheses, even though they don't look the same as those hypotheses we've been doing prior to this point. So viewing pref and genders are dependent. And h sub 0 says viewing preference and genders are independent. And then, being a little bit unlike those testing a hypothesis problems we have done prior to this point right here, then for this kind of testing of a hypothesis, we don't need to worry about being a right tail or a left tail test. So obviously, we don't need to indicate whether we're going to use a right tail test or a left tail test, because we're going to run a slightly different style of testing it. We're going to be utilizing a different route of work. But now we are ready for getting into testing our hypothesis right here. So the goal, again, to see whether we can successfully reject h sub 0 or successfully support h1 due to having strong evidence. So we want to definitely find out whether our sample as a table is showing strong evidence. That's the ultimate goal. And now let's look at another truth on any two-way table here. So the table that we're currently seeing here, any of these count in the intersection between a column and a row that's before the total column and before the total row here. So any of these counts here, say for example the count that's right now being 50 in the column for Lone Ranger and in the row for boys right here. And systematically we can call this is row 1, column 1 right here. So this count right here is being regarded as the observed count because it initially came as how the table was originally presented. And so now the term for that, in row 1, column 1, we have an observed count that was indicated to be 50 because this was a count that was already observed and given in a table. So that's what it means by being observed count. And so for our convenience, we use the symbol capital O with the subscript 1, 1 to indicate observed count in row 1, column 1. So observed count in row 1, column 1 currently is given as 50. And that's what's indicated here in our row 1, column 1. So the same with any other row and column right there. So row 1, column 2, for example. We're now looking at O12 equals 30. And so row 1 again, but column 2. Okay. We found observed count to be 30 as from the table. So the way we're writing that now, O1, 2, and that's 30. So that's just the way how we are indicating with these values. So in this table, and as I said earlier, before the total column and above the total row here, then we're looking at right now as 6 different, we have 1, 2, 3, 4, 5, and 6 different observed counts. Okay. But now the real truth that I was about to say now is that the same table here, but there's another kind of count that always existed. So let me now bring up an empty table as following. And so the reason I stayed away from the row, the total row and the total column here is that because the total row and the total column here has its own importance. Say, for example, this column right here is listing it's the total of all the boys. So because the count here could be different in other samples. So we're looking at a sample of 300, but maybe in another sample, in a different sample, still 100 for the boys and 200 for the girls. There could be different counts being distributed here among these entries. And that's why for whatever I'm doing to this table, I'm only going to focus to these inner entries of the table and stay away from the total row and the total column right here. So the other kinds of count that I was in the middle of saying now is that you see now if I completely go to a table where all of these counts are completely empty right here, but I still retain, let's say in my sample there are 100 boys, 200 girls, and among these children in our sample there are still that same number of 100 viewers who prefer watching Lone Ranger, and there are 110 viewers. Now I don't know how many boys and how many girls in here, but I know that there are still 100 viewers who prefer watching the Sesame Street TV show. And then there are the other number is 90 viewers among the sample here, 90 children among the sample here prefer watching The Simpsons. So then there's another kind of count that can always happen, and we can always purposely find that exists in each of these entries here. And those counts are being regarded as the expected count. And so the term I'm using earlier is called the expected count. Okay, and so expected count, I use a capital letter E for this. That's E is for expected. But so here, let's say if we're looking at row 1, column 1, then very similar to how I explained about the observed count, the expected count that happened in row 1 and column 1 is notated as E with a subscript 1 for row 1 with a comma and another subscript right here for column 1. So E11 right here is indicating the expected count that happens in row 1, column 1, which is the expected count that I'm about to find. For any table, as long as we know the total column and the total row right here, we can always come up with the expected count right here. The difference between expected count and observed count is that observed count is whatever comes right here in our sample being distributed. The counts are distributed among these, but expected count we can always theoretically calculate based on the column, the total column and the total row that's already known right here. So now back on my board here, this is the way how we're going to calculate expected count for row 1, column 1. I am going to look for row 1 total and multiply that with column 1. So COL is short for column, so column 1 total. I am going to multiply those two numbers and divide by the total sample size. In our case here, being 300 is our sample. And so now one more time looking back at our at our table. So to calculate the expected count in row 1, column 1, our row 1 total is 100 here, and our column 1 total is also another 100. So that means Now back on my board, we can proceed the calculation as following. 100 for row 1 total. I am going to multiply with 100 for column 1 total. And that multiplication is now going to be divided by, that product is now going to be divided by 300. And so now calculation of mine shows 33.3333 and a lot longer. So that means now I can put this expected count right here into my table. And so for this entry, being a boy and being a viewer who prefer watching Lone Ranger, then according to the table, the distribution of the data this way so far, that within the sample we know that we only know we have 100 boys and 200 girls in the sample, and further we know that there are 100 of these children who prefer watching Lone Ranger, and 110 of these children who prefer watching the Sesame Street, and so on, then we can theoretically expect that the count for being a boy and being a viewer who prefer watching Lone Ranger is only a 33.3333 count. And you can already start noticing some difference between the expected count that we're currently having here and the observed count that originally came with the table. All right. But now, so allow me to proceed to the next entry here. So what about, let's now move over to row 1 and column 2 over here. So as I said, in any of these entries before the total column and above the total row here, then we can always find the expected count. So now right now, to be clear again, I am going to be calculating the expected count that can happen theoretically for being a boy and at the same time being a viewer who prefers watching the Sesame Street, or it's row 1, column 2. So now on my board, row 1, column 2, the expected count is a capital letter E. Row 1 is a subscript 1, is the first subscript 1 in a pair, and column 2 is the second one in the subscript pair. So E1, comma 2 is my expected count in row 1, column 2 entry. And so very similar to the way how I have done earlier. I'm going to look for, we're still in row 1, so I'm going to look for row 1 total and multiply for that row 1 total with column 2 total this time. And divide that by my sample size. And so that means my expected count for row 1, column 2 is going to be, and now according to row 1 total, I'm looking at 100 being my row 1 total. But for column 2 total, we're looking at this value right here being 110. So that means now we're looking at 100 for row 1 total, multiply with 110 for column 1 total, and we're still dividing that by our total sample size, 300. Calculation of mine came out to be 36.6667, because the truth is this is 6666, infinitely many 6 right here, and a lot longer, but for now I round to 4 decimals, so that's why the last value here is a 7. And that is how I put that expected count into my entry right here for row 1, column 2. So again, let's quickly look at the difference between this expected count in row 1, column 2 and the actual observed count right here. So observed count in the same entry that happened in our original table is 30. So row 1, column 2 in our original table was 30. But now expectedly, I count there should be 36.66666. And so now let's advance to row 1 and column 3. So on my writing board again, row 1, column 3, the expected count is notated by capital letter E at entry 1, 3. So 1, comma 3 is written as a pair of subscript right there. And so now just very similar, and at this point we're going to start drawing some generality of how we can calculate expected count at any entry right here. We're going to go with row total. So row 1 total still, and multiply with column 3 total, and divide that by our sample size. And that means in the next step, for the actual calculation, I am going to go for, now quickly looking back at our table here, then row 1 total is a 100, but row 3 total is a 90. So 100 times 90. So 100 is my row 1 total times 90 is my column total, and I'm going to divide by 300. So that will give me, according to my calculation, 30. So that means in my table, I expected that for being a boy and being a viewer among these children who prefers watching The Simpsons, then we have an expected count to be 30. And now that we're done with this row 1 right here, then let's get ready for, now we can advance to the next row down and return back to column 1. So here we are at entry row 2, column 1. So now on my writing board, row 2, for row 2 and column 1, which is what we're heading to, then the symbolic expression for that, E21. And now again, I'm repeating that formula, but with different row entry. So row 2 total this time, multiply with column 1 total, and we're still dividing that by our sample size. And so to get into the calculation itself, now we can again look back at our table on the computer screen right here. So now right here at where we stand at row 2, column 1, and row 2 has a row total being 200, and this column 1 has column total being 100. So back in my board, I'm looking at row 2 total being 200, and that is going to be multiplied with 100 for column 1 total. And now the product there is divided by 300. Calculation of mine shows 66.666667. So it should have been a lot longer, but I decided to stop here at 5 decimals, so I round that to 7. And that is the expected count that should happen, that can happen in this entry at row 2, column 1. And so quickly looking back at our observed count. So now when it was row 1, column 3 right here earlier, then our expected count that we calculated was 30. And now look back at our observed count that initially or originally came with the table, it was only 20. So each one of these, so in the idea so far now is that in each of the entry, there's always a slight or maybe some far difference between observed count that came originally with the table and expected count. So any of these expected count is very likely to be, somehow different with the observed count, the count that already came in the table. Okay, so now particularly for our case here, we're looking at row 2, column 1. So the expected count that we just now calculated is 66 point, a lot of sixes here, whereas the observed count was only 50 in that row 2, column 1. And so that's what I need anyone viewing this video to notice. There's always a difference between observed count and the expected count. The difference could be a little, or it could be large, or sometimes the difference can also be a 0. Sometimes we can have expected count equal exactly the observed count. Anything can happen. But now let's look at expected count for row 2 and column 2. So back on my board, expected count for row 2 and column 2, I am going to use a symbol capital E with a pair of subscript 2, 2. 2 is for row 2, and 2 here is for column 2. And so now I'm going to go with, that means we have row 2 total, multiply with column 2 total, and divide that product by 300, our sample size. And so now calculation comes out for the setup. We were looking at row 2 is being 200 for row total, and column 2 is 110 for column total. So our setup here is gonna be 200 times 110, and we're dividing that product by 300. And so now calculation of mine came out 73.3333, and a lot of threes. And this is now the value that's needed to be entered into row 2, column 2 for the expected count. So we have one more to go. So far we have made 5 of those expected counts so far, and it's now time to advance over to expected count for row 2 and column 3. All right, so now row 2, column 3, E23. I'm going to look for row 2 total and multiply that with column 3 total, and divide the product there by the sample size 300. And I have been switching back and forth between the two, between my writing board and the computer screen often enough, so anyone might have seen that, might have memorized the table already. So row 2 total is a 200, and column 3 total is a 90. So we multiply these two and divide by 300. Final calculation of mine came out 60 as the expected count for row 2, column 3. And so now if we're quickly looking back at the table on the computer screen here, then I enter that table. I enter that value into this entry row 2, column 3, and looking back at the observed count for the same entry is 70. And so we can see some small difference. The difference here between 60 and 70 for observed count is not too big, but in the end, at any of the entries in our two-way table, there will always be some kind of difference between each observed count and the corresponding expected count. And so let's come up with some generalization here. Expected count at any entry. So let's say at some ith row and jth column. So that's what the EIJ is for. So the way that we have been doing is that we're going to go with the ith row total, or the total on the ith row. We're going to multiply that count with the column total on the j column. So the jth column total, that product there is divided by n, the total sample size. And so this is the formula that we use to calculate the expected count that can happen. And we can always calculate expected count on any entry before the total column and before the total row on any two-way table. So that's one thing I have to re-emphasize again. And the way to calculate the expected count on any entry is here. And so this sample size here is just that number that always appears at the very bottom right corner of our table, if that's the way how we organize our table. And so now, after spending some significant amount of time finding the expected counts, then now we can formally say that finding all expected counts throughout all entries of our two-way table is going to be our first step in testing this hypothesis. And so again, let me swing back on the computer screen to show the expected count, all of the expected counts that we have calculated. So the expected count for entry row 1, column 1. That is 33.3333 and a lot longer. Then we have found back on the computer screen here with my table the expected count at row 1, column 2. We now have row 1, column 2, and that was 36.66667 and a lot longer. And so we already have found 6 different expected counts. So that's, again, the first step in testing our hypothesis here. And so after we have successfully found all expected counts and put that in a separate table over here, now let's have some direct comparison between this current table here that contains expected counts and the original table that contains all of the observed counts right here. Then we can see that any of the expected counts here is making some difference with its corresponding observed count. And so now, after observing the expected counts and the observed counts right here, then we can see as a generality that usually the expected count is different from the observed count in an entry. But there could still be cases where the expected count equals exactly the observed count in an entry. And so now, upon realizing the existence of the differences between expected counts and the observed counts here, we come up with the next kind of calculation, and that is regarded as the next step right here. So let's say for row 1, column 1, I'm going to have observed count in row 1, column 1, minus the expected count in row 1, column 1, which was that 33.3333, and a lot longer. Our calculators in these days are usually strong enough, so I highly recommend leaving these values the exact same way how it is, with the complete precision that came straight out from the calculator. But now 50 is the observed count, subtract the expected count here, and these are all in row 1, column 1 entry. We're going to square that difference and divide that by 33.3333 and a lot longer. So this value here, whichever it will come out, is referred to as the components. And for short, symbolically, I call that COMP, components in row 1, column 1. So it's a value that's made by taking the square of the difference between observed count and expected count, then divide that by the expected count itself on the current entry. Current entry here is row 1, column 1. And so what I did here in row 1, column 1, particularly as a formula, is the observed value from row 1, column 1, subtracting the expected count in row 1, column 1, square that difference there, and divide it by the expected count in row 1, column 1. And we refer to this calculation as the components value for row 1, column 1. So now with the actual values here plugged in, then my final component 1 is calculated as 8.3333 and a lot longer. So this is component 1 that came out from subtracting the expected count 1 from the observed count 1. Then square the difference and divide it by the expected count in row 1, column 1. Then we would record that value into another table, where this table here, I left all of these entries empty right here to make it ready for filling in with all of the component values. So our first component value that we have calculated, component 1 is now being recorded here. And so now we're ready for the other ones. So now I'm heading out for components 1, 2. I'm going to stay in row 1, but now switch over to column 2. And so to get there, I need to take observed count in row 1, column 2, subtract expected count in row 1, column 2, square that difference, and divide it by the expected count in row 1, column 2. And so that means now observed count for my row 1, column 2 is 30, whereas expected count for row 1, column 2 was 36.66. So now I'm looking at 30 minus 36.6667, and a lot longer. I actually, even though I'm rounding here, but I actually use the full precision, so it's with the infinite 6 in the decimals here. And divided that by 36.6666. Maybe I shouldn't leave that last 7 anymore. So now final calculation of mine came out, and again, I'm keeping all of these in full precision. So now my final calculation of mine on this expression would come out to be, and again, I'm keeping full precision on each one of these, even though I'm writing only with 3 decimals. So the calculation came out 1.2121, and a lot longer. And now for components, unless being specified otherwise, usually I'm going to round to 2 decimals. So this final component for row 1, column 2, I'm going to round to 1.21. And so now on my computer screen right here, back to our table. Now I'm filling in the component count for row 1, column 2 right here, 1.21. And I should have also mentioned earlier that this 8.3333 earlier, now I rounded that down to 8.33. Because as I said earlier, unless being specified otherwise, but for most of my video lectures regarding the chi-square test, and I'm going to be rounding these component values to 2 decimal places. All right, so now we are heading out for row 1, column 3. And so now the component value on row 1, column 3 is found by observed count on row 1, column 3, subtract, minus expected count on row 1, column 3, then square the difference and divide it by the expected count in row 1, column 3. And that now brings me to 20 for the observed count. In row 1, column 3, I am going to subtract 30 as the expected count, then square the difference and divide it by 30. My final calculation shows 3.33. So it should have been a lot longer, but as I have already explained, I am going to round all of my component values to 2 decimal places, unless being specified otherwise. And so now 3.33 is going to be entered in our empty table here for row 1, column 3 entry. So let's now move out to the next one, row 2 and column 1. The components in row 2, column 1 equals observed count in row 2, column 1 minus expected count in row 2, column 1, square the difference and divide it by the expected count for row 2, column 1. And so in that way, I had 50 for observed count in row 2, column 1, and I had 66.6666 and a lot longer, and all the 6 here. Square the difference and divide it by 66.66666. So final calculation comes out to be 4.17. This is after I rounded down to 2 decimal places. The original value was a lot longer. And again, unless being specified otherwise, for all of the component values throughout this video lecture and my other lectures will be rounded to 2 decimal places. And so now I enter that value, the component value in row 2, column 1, into it designated entry. And let's now move over to the next entry, row 2, column 2. Component value for row 2, column 2, we're going to take observed count minus expected count in row 2, column 2, square the difference, and divide it by expected count for row 2, column 2. Observed count in row 2, column 2 was 80, and expected count was 73.3333, and a lot longer. Subtract the two, square the difference, and divide it by 73.3333. My final calculation came out to be 0.61 after being rounded to 2 decimal places. And so now I am going to enter that value, that component value 0.61 into my empty table here for row 2, column 2 of my current table. And now we're moving out to the last component value. Component value for row 2, column 3. I'm going to take observed count in row 2, column 3, subtract expected count in row 2, column 3, square the difference, and divide it by the expected count in row 2, column 3. As far as the actual value, observed count in row 2, column 3 was 70, and expected count here was 60. I'm going to take the square of the difference here and divide it by 60, the expected count in row 2, column 3. Final calculation came out to be 1.67. And again, this is after I have rounded to 2 decimal places. And so now I am going to enter that last component value into its appropriate entry in our current table. So row 2, column 3, this is where we enter our last component value, component 2, comma 3. So as a generality, finding any components is done by taking the observed count in the current entry, subtract the expected count of the same entry, square the difference, and divide it by the expected count. And that's the formula how we calculate the component value. So specifically in our case, since we're having a two-way table, so any component's value at any ith row and j column, this is the symbol of component at ith row and j column, will equal observed count in ith row and j column minus the expected count in the same entry, square the difference, and divide by the expected count in the current entry. So these are the two formulas, and primarily this is the formula for our case working with a two-way table. That's how we generally find component values. And so as far as the steps to test our hypothesis here, then after step 1, finding the expected count, we have gone through the second step just now by calculating all components, or a lot of time I call these the component values. So again, recall for yourself, components at any entry, ij, is done by taking the observed count in the current entry minus the expected count in the current entry. square the difference, and divide it by the expected count in the current entry. And now that we have had all component values calculated, the next step now is to calculate a value that's so-called a chi-square value. So it looks like a script of x, but this is called a chi-square value. You don't need to learn how to write this chi-square symbol from me. You can just hop onto the internet and type in the value chi-square. Type in the name chi-square, and there will be a website that shows you how to draw this symbol successfully. But that symbol here is called chi-square because this symbol itself is called chi. So this is chi. And so to calculate chi-square, we're going to sum. The generality here is to sum all components. That's how we're calculating chi-square. And so let's one more time look at all of our components that we have found and put it on our table right here. So we've gone a long way from the original table that was given here that only had observed counts. Then we calculated our expected counts. So I switched to a different table here, pretty much the same total row and total column right here, but these entries inside of those are all different values because these are the expected counts. Then we came to a different version of our table, which lists all component values. And you have seen the work just earlier. And so now the next step here is to calculate chi-square by adding up all of these component values. And so now back on my writing board here, my first component value from the table we have seen is 8.33 because this is row 1, column 1. I am going to add to the next value being 1.21. This is row 1, column 2. And I'm going to add to the next component value being 3.33. And this is row 1, column 3. And I'm adding to the next value. So at this point, we're moving down to row 2 right here. So row 2, column 1 has component value 4.17. So I'm adding all of these as set by the formula over here. Chi-square is found by the sum of all components. Now I'm going to add to the next component value. So from the table we have seen earlier, 0.61 is the component at row 2, column 2. And now we're going to add to 1.67 being the component value at the last entry, row 2, column 3. And the sum of all these component values is referred as the chi-square value. Final calculation of mine came out to be 19.32. And so back in these components, since I said I rounded all of these to 2 decimal places, and usually I keep that convention for my own lectures about keeping all of these to 2 decimal places. So normally I would do as well by rounding the final chi-square to 2 decimal places. So that's our final chi-square value in 2 decimal places, which is what I usually round to. And so now looking back as far as the steps into our work testing the hypothesis about independence here, then after step 2, we advance to calculating the chi-square value as just now seen on my writing board here. So after calculating all components, we advance to calculating the chi-square value. And the value for the chi-square, so chi-square is found by the sum of all components. So now that we have calculated our chi-square value to be 19.32, then now we need to know that our two-way table currently is having 3 columns and 2 rows right here. And again, as I have always been saying, we will never count the total column and the total row here. So officially speaking, our table only has 3 main columns and 2 main rows right here for the boys and the girls. So in that way, our current two-way table has degrees of freedom, which is now 2 rows minus 1 times 3 columns minus 1. And so this will give us degrees of freedom. So df stands for degrees of freedom. And so the degrees of freedom for our two-way table. And that's the way how we're calculating degrees of freedom for two-way table. This is going to be 2. So we're looking at degrees 2 here. So generally speaking, degrees of freedom for any two-way table is found by number of rows minus 1, then multiply with in product with number of columns minus 1. So now that our degrees of freedom for this table is a degree 2. But sadly, degrees of freedom has never been a formal step. So even though it's some valuable information, but I wouldn't categorize this as a step after calculating the chi-square value. The next big step now is to calculate the p-value for our current table. And the idea again of the p-value is to decide whether we have strong evidence, whether our table is showing strong evidence. This is decided by that p-value. So p-value for our table is calculated as following. I am going to fire up a probability calculation that is looking for a chi-square value greater than or equal 19.32. And so have a close look at this setup right here of how I calculate the p-value. It's a probability problem, and I'm looking for among all chi-square values out there, what's the chance we're going to find a chi-square value being greater than or equal 19.32. And this inequality that we use in our probability statement is always, I have to put it in red ink here, always right tail. It's always a right tail inequality pointing to the right hand side. Right, so that is something to know. And so to calculate this p-value, or primarily to calculate this probability where we find a chi-square value greater than or equal 19.32. So this is already our chi-square value, but we want chi-square to be above this value. Then we're going to use a technology. So in my lecture here, I'm mostly going to stay with the TI-83 and 84 calculator. So now on my TI-84 calculator, here's how I can find the command that can do the work here. I'm going to go second variables, and I'm going to scroll down and look for option that says a chi-square. So chi-square CDF is right here. Chi-square CDF. I'm going to hit enter to start executing to call up the command. So here's the way how it looks. Back to my on my writing board a little bit. So the inequality here is, as I already said, it's always right tail. So that means this value here is our low end, and so it's going to be always the same way like this for any other problem right here. So that means our chi-square that we have found will always be the low end. So now back on the calculator itself, I'm going to enter 19.32 for low end of our chi-square CDF. But now upper end, I'm going to go 1E99. And then I'm going to hit enter. For degrees of freedom, I'm going to be enter 2. I'm going to be entering 2. And then I'll hit enter. Now, some other calculators, some earlier versions of the TI-84 or the TI-83 calculator, after calling up the chi-square CDF command, it will be printed directly on screen instead of seeing a menu like what you have seen earlier. So in that way, you are going to enter in the values manually. So 19.32 for the low end. So low end always comes first in any of the chi-square CDF command throughout the TI-83 and 84 calculator. Upper end separated by a comma. And now 1 E99 and another comma, and the degrees of freedom 2, and close the parentheses. That's how we can complete the chi-square CDF command in the early TI-84 or the TI-83 calculators. And now we are ready for executing the command to find our value, to find our final p-value. So this is what it reads right here, 6.3784 and a lot longer with an e minus 5. So that means this p-value that we have calculated equals 6.37845 and a lot longer with an e minus 5. I have discussed this before in earlier video lecture, but I can mention again that this notation here is the way how the TI-83 and 84 calculator is expressing, but it means 6.37845 and a lot longer, but times 10 to the negative 5. And so on in the end, this means our final answer really is in decimal, 0.0000, 4 zeros and a 6, 37845 and a lot longer. And so now for p-value, just like any other video lectures, anytime it comes down to p-value, I will round it down to 4 decimal places. And so in this case, my final p-value here in 4 decimal places, 0.0001. And that is our final p-value. So now recapping what happened. Our final p-value was calculated to be 0.0001. And now that we have had our final p-value, then just like any other testing hypothesis problem we have done prior to this point, then final p-value 0.0001 will be compared with the significance level to find out whether we're having our p-value falling below the significance level or greater than. That's what we want to know. And so all of these here are the steps that are taken after calculating the chi-square value in testing our hypothesis about independence. So now back to the question that I have addressed earlier. We are given a significance level 0.001. So that now means our final p-value is to be compared with significance level 0.001. And direct comparison now clearly shows that our p-value is well below this significance level, 0.001. So that means further that the sample as the given table this sample, the original table that we've had right here, is an unlikely sample. And that's making the sample strong evidence to, one thing to say, to reject H sub 0. Or we can also say to support H1. And then back to the question itself, ultimately speaking, it is a yes or no question. Let me clear out these highlights right here. But is the sample showing strong evidence? So as a yes or no question, and now apparently we have strong evidence. So our answer to the question here is yes. And so now let's roll back to the beginning of our problem, and let's try to understand some brief interpretation of the result here as far as how the steps connect. And so the idea now is that after observing the table, we came up with an alternative hypothesis suggesting that viewing preference and genders are dependent. And this suggestion is an argument against some other statements as a null hypothesis, saying that viewing preference and genders are independent. And so the logic of the disproving hypothesis comes out as following. Think about if we started out accepting h sub 0, then consequently the entire table will produce all of the expected counts as calculated here. So these expected counts came out as a consequence in accepting h sub 0. So if h sub 0 really was true about the two categorical variables are independent in our table, then we produce those expected counts as we have already calculated in here. And so I have to admit that a lot of theoretical explanation about where the formula came out from, the formula for expected count. So expected count, as a reminder, expected count on any entry is the row, the ith row total, and that's for short, row total times the column total, the jth column total divided by n. So now back to what I was saying, how this formula was derived and how independence is connected with the expected count here. All of that details must wait for a more advanced course in statistics. So here we can just take that simply as a direct consequence that anytime we assume the validity of independence between any two categorical variables, then the two-way tables will have the expected counts, and the expected count can come out by performing these formulas on each entry, this formula on each entry. Then consequently further, those expected count that we found will allow us to calculate the components values as the next consequence. Then consequently in the next step it produces the chi-square. So ultimately accepting independence between the two categorical variables here lead to having this chi-square value. And our table, depending on the number of rows and columns produced for us, on another hand, a degrees of freedom. But then the further consequence now is we're going to lead to, once we've had this calculated chi-square value, it leads to a final value for p-value. And so the calculation and the comparison with the significance level between the final p-value and the significance level is what decide that whether our sample as the table can be unlikely or not. And so obviously in this particular problem right here, consequently we led to having a chi-square like this in our table, which happened in our table, but having a chi-square like this is usually very low chance. And so it's so low chance that the sample itself like this is very unlikely sample. And unlikely sample means if we accepted independence, then it's very unlikely to have a sample like the table we have. And so being unlikely sample leads to being strong evidence. So now ultimately strong evidence means we reject that h sub 0 cannot be true. It cannot be independence between the two variables. There has to be some kind of dependence going on. And now I have to also be clear again, even though I mentioned earlier, but now as we said, we support the belief that there is some dependence going on in this table. But keep in mind again, I did not appoint to any specific dependence. There can be a lot of ways how the two variables here are dependent on each other. So that's not what we are looking for in here. We're not looking for in which way the two variables are dependent on each other. That's not what we're doing. We only say that according to the test result here, we are supporting H1. And as H1 is suggesting that viewing preference and genders are dependent, all we know here is that there will be some kind of dependence going on here between viewing preference and genders, and that's all we know. But we're not specifically pointing to any particular kind or in which way the dependence is.